in the name of the Almighty, the compassionate, the merciful. We are still in the phase of the calculation of derivatives, the antiderivatives. We have actually explained, we went through the first method, which we call substitution. Substitution, in fact, is the most famous, or one would say the most widely used method among the methods for calculating antiderivatives. Today we shall speak about the integration by part. This is our second method, and this method is by far the most, one would say, the most powerful and competent among all methods for calculating antiderivatives. Usually this method of integration by parts, how would one know that you need integration by parts? Usually when you see your function as a product of two categories or two different types of functions, like for example you have one algebraic and one transcendental function, then you are bound to use this method of integration by parts. Like for example you have the integral, for example, of x times sine x dx, or the integral of x times e to the x, or the integral of, for example, x ln x, etc., or the integral of e to the cosine x, the x multiplied by cosine x dx. You realize that all these functions here are functions that are product of two functions of different nature, an algebraic one and transcendental one. Same thing with the other. These two functions are not both algebraic, yet of different nature. Suppose, for example, I have a function of this sort, then logarithm alone. You still would need integration by parts. Or, for example, sine minus 1x, the arc sine of x dx. This one as well, this is in fact a product of two functions, because if you substitute x is equal to sine y, you end up with this is equal to y times dx, which is cosine y dy. So in fact, again, it's the product of two, one algebraic and the other one is transcendental functions. So in fact, when you see a function of this sort, you say that you have to resort to integration by parts. The theory of integration by parts, as we shall explain, first we shall outline when is the theory needed, and then the main theorem, and then a technique which is much simpler, and then we come to the reduction formula. Now the formula which we shall use, in fact, relies upon this this proof here, or this is how we produce our formula of integration by parts. You have, for example, the derivative of two functions like this. It's equal to f prime of x times gx plus f of x times g prime of x. So you get here, if f of x g prime of x on the left hand side, it becomes equal to d by dx, the f of g of x times g of x minus f prime of x g of x. And in fact, if you integrate both parts, you get an expression of this sort. G of prime of x dx is equal to the integral of this of a derivative is equal to the function directly. So f of x times g of x minus the integral of f dash of x times g of x dx. And here, actually, what you do is that you didn't get something new, in fact, from this expression. But it tells you something. It tells you that if you can find a product of two functions such that one can be one differentiated, vanishes, for example, or is reduced in degree, then you come up with a formula which is actually easier to integrate than the previous or original one that you started from. For example, suppose you have an integral of x e to the x dx, and you set out what? You set out, for example, this is you call this v, which is e to the x, and you call this u, for example, which is equal to x. So now you have what? You have f of x times g dash of x dx is equal to, as our formula runs, is equal to f of x, which is x times v g of minus the integral of f prime, the derivative of x, which is 1, times du dv. I'm sorry, you have here times v, which is e to the x dx. So in fact, this becomes equal to x to the x minus the integral of e to the x, which is directly e to the x. You don't neglect the c. You don't forget the c. So in fact, here what you did is that you relied upon something which is important, is that you see that here there is an x. Once you see an x, you try to take this as f. And once you take this as f, you end up with what? This is f of x again, and g of x is equal to e to the power x, and g prime of x is equal to what? G prime of x is equal to e to the power x dx. So in fact, this is equal to f prime j dx, which is in our formula, is equal to f of x times g of x minus the integral of f prime of x, which is 1 here. When you derive this, the derivative of this is equal to 1 times g of x. But here you gain something. Your profit here, you benefit from the fact that f prime is equal to 1. So reduce your formula from x e to the power x to 1 times e to the x. In fact, this can be made much simpler. Here it is. This is how we derived. The integral of f times g dash is equal to f times g minus the integral of f dash g. But in fact, you may put it in a much simpler way, thanks to again to Leibniz. Leibniz said that the integral of f of x times g dash of x, if you take f of x is equal to u, and v of x v is equal to g of x. So in fact, what you have here, this becomes what? This becomes u dv, because dv is equal g prime x dx. So in fact, this becomes u dv. Whereas the integral of f prime x g of x dx is equal to what? G prime x g of x is equal to what? Is equal to the integral, this is the integral, is equal to what here? Is equal to v du, because du is f prime x dx, so this integral of v du. So in fact, you have now your formula in an easier form. You have the integral, this integral u dv is equal to what? Is equal u times v minus the integral of v du. In fact, this is another way of writing your expression. The expression that was on the previous slide, you can put it in this way. Both are exactly similar, except that this is less complicated in a way. It goes using the differentials of Leibniz. And in fact, you need not even obtain this from the previous result. All you have to do, you can do it this way. Du uv is equal to u dv plus v du. And even this is differential of life. Even if you divide by dt, you get what? You get directly d uv by dt is equal to u dv by dt plus v du by dt. So in fact, you get here u dv by dt is equal to d by dt times uv minus v du by dt. And in fact, if you integrate this with respect to t, you directly obtain, you have here, you integrate with respect to t, and you get the integral of u dv is equal to uv minus, I'm sorry, here without integral, because the integral of duv minus the integral of the v du. So in fact, your formula which you can obtain, you don't need to go and allocate it to f and j. You directly have a sort of a formula which is direct in the what we say in the form of Leibniz, or in the notation of Leibniz. This in fact allows you to carry on any integration. Suppose, for example, you wish to integrate x e to the power x. Which is u and which is v? X e to the power x dx. We try to find something so that it comes out easily at the end. It is reduced. So here, for example, I may take this is u, and x is equal to u, whereas e to the x is equal to v. And you integrate what? You integrate, in fact, u dv. So u dv, this is equal to u dv. In fact, so it's equal to u times v, which is x times e to the x, minus the integral of v du. So here v, it's e to the power x, du, d what? Dx. So in fact, it becomes much simpler. Again, you have here x e to the power x dx. You try to put it in a way such that it is when you apply the formula of Leibniz, and actually integration by parts is due in history to Leibniz, you end up with a form which is simpler. So you have to choose your u and v in such a way that you end up with a reduced formula. Instead of having x e to the power x, you have e to the x dx. So which one you prefer to take as u and which as v? If you take as a matter of fact this as u and this as v, and you try to integrate this one, you get half x squared, so it becomes more complicated. So here you directly obtain this formula here plus c, which is the integral. And this is how it goes. You end up with a formula like this. Again, e to the x times sine x dx. Here again, which one you take? Suppose we do it this way on the slide directly. Suppose you take u is equal to sine x and v equal to e to the x. So you get here, this is equal directly to what? Here, u is equal to sine x and v e to the x. So this is u dv in fact. So u dv is equal to what? The integral of u dv is equal to u times v. So this times this, which is e to the x sine x, minus the integral of v, which is this, d sine x. But d sine x is equal to what? Is equal to cosine x dx. And then you carry out the same integration again. You take this as u and e to the x as v again. And you end up doing what? You take e to the cosine x and v e to the sine x. And in fact, this is the formula which we ended with. Here, the integral of e to the cosine x dx. So e to the x times cosine x dx. So again, it is equal to u dv minus the integral. We have another minus because the cosine, d cosine is equal to minus sine x dx plus here. So you get this formula here. But again, here again, when you contemplate this, you find out that your unknown, which you seek to calculate, which is your integral, is again is equal to something minus the same integral. In other words, twice the integral is equal to this minus this, so that the integral is equal to half this expression. In fact, this u and v business, you can always do it this way. But there are some other methods that one have seen in some books. Because the student, in fact, in engineering, each time is asked to calculate integral by parts, which he'll find enormously in his study of engineering, Fourier series, etc. All this deals with integration by parts. So there used to be, I've seen once, a table of this sort. For example, suppose he wants to integrate x times e to the cosine x. So he puts x here and e to the x here. And then he integrates this. So you get this. You keep integrating it. While here you keep differentiating it. So you get 1 and you get 0 and it finishes. And then you multiply your integral x e to the x dx. It becomes equal to what? You multiply this by this. And here you just invert the sign. So you get x e to the x minus e to the x plus, of course, c. Again, suppose you wish to calculate the integral of x square sine x dx. So x square sine x dx. Of course, you do it by parts. You take this is equal to u, and this is v. V is equal to minus cosine. And you do it in this way. But you can also do it, you integrate it once. You got minus sine, and then again minus sine, and then again cosine. And then you differentiate this to x, and then 2, and you get 0. And then you keep multiplying, and you invert the sign. This goes with this one. You get minus x square cosine x. And here you invert the sign, so you get plus 2x sine x. And finally, you get plus 2x, 2 cosine x plus c. If you have something like, which doesn't end like this one, sine x dx, it's not much different. All you have to do is that you put x and sine x. And here you have, you integrate it once, you differentiate, you keep differentiating, but it doesn't end, in fact. It doesn't end. So here you integrate this one, you get minus cosine x, and then minus sine x, but you keep losing something that you multiply this by this, and this by this. Since it doesn't end, you get this with this one. So you get, this is equal to minus e to the x cosine x, and this you invert the sign, plus e to the x sine x, and then minus the integral of e to the x sine x dx. This is what we have this is what you obtain. But you remember something. This is the integral, which is the unknown. And you see it here again, I. So you have twice I when you get it, when you shift this to the left-hand side, is equal to e to the x times sine x minus cosine x. So what is your integral equals to? Is equal to half this expression, and you don't forget the c. And this is actually the way you do it. In fact, each time we run into integrals of this kind, and you wish to check which is u and which is v, like this one, for example. Here, for example, you can take u is equal ln x, while v is equal to x. So this is the integral of u dv is equal to u times v, which is x ln x, minus the integral of v du. So v times d ln x, which is 1 over x. And this you get, you end up with the integral of 1, which is again minus x. So you get of this result. But in fact, there is another way of doing this, and this is I teach to my student. Instead of saying the integral of u dv is equal to uv minus the integral of v du, you get it in a much simpler way. You say the integral of a product of two functions is equal to the antiderivative of one times the second one without change, minus the integral of, again, the antiderivative of the first one, but this time not times the second one, times the derivative of the second one, and this is how it goes. Suppose, for example, you wish to integrate ln x dx. So your best thing is to put here 1. You get the integral of the first one, which is x, times the second one without change, minus the integral of the first one, again x, times the derivative of ln x, which is what? 1 over x dx. And this cancels out to obtain 1. The integral of 1 is equal to x, and you end up with a formula of this sort. So actually, this is the easiest way of doing it. Instead of choosing a u and v, and which is u and, v, and which is me, you end up doing it this way. Suppose, for example, you have the integral of, for example, x times sine x dx. Here again, the integral of 1, we integrate this one. Why? Because this one, when differentiated, it vanishes. You integrate this one, you get minus cosine x. Times the first one without change, minus the integral of this one. So you change sign because you get minus cosine x. Times the second one, times the derivative of the first one here, which is 1 dx. So you end up with what? Minus x cosine x, plus the integral of cosine, which is sine x dx, plus c. And if you wish, wish to check whether this is correct, all you have to do is to differentiate it. If you differentiate it, you end up with x sine x. Again, suppose you wish to calculate the integral of cosec cubic x dx. How would you do that? Usually when you integrate cosec cubic x, there is no other way except the integration by parts. Here what you do it, you have to know this. You have to know that there are functions that you cannot integrate it without by parts, like sec cube, cosec cube, and of course product of functions which are one, for example, algebraic, and the one is transcendental. I mean, like product of functions of different types. So this one comes as integration by part. You put it this way: cosec square x times cosec x dx. And here, of course, you can follow your u and v approach. You can take, for example, this one is v. You can take v is equal to minus cotangent x, because d of minus cotangent x is equal to cosec square x, while u is equal to cosec x. So in fact, this is what? This is u dv is equal to u times v cosec x minus cotangent x minus the integral of v, again, plus here, you invert this one, cotangent x, times the derivative of cosec, which is minus cosec x cotangent x dx. In fact, there is no point of, you can actually, what you can do is that instead of doing all this mess, you can directly apply our method of integration by parts. You integrate one. Here, for example, you skip this step here. You come from here to here directly. You integrate the cosec square. You get what? Minus cotangent. Times the second one without change. Let's do it properly and in detail. You have here cosec square x times cosec x dx. You integrate one. You integrate this one. You get minus cotangent. Times the second one without change. Minus the integral of the first one. Of this one again, which you get minus cotangent. So we invert this sign, times the derivative of the cosec, which is what? Minus cosec x times cotangent x dx. And now it's a little bit complicated, but it's not actually, because you can write it this way: cosec x minus the integral of cosec x times cotangent square. What is the value of cotangent square? Is equal to cosec square x minus 1 dx. So in fact, this becomes equal to minus cotangent x cosec x minus the integral of cosec cubic x plus the integral of cosec x dx. Now we watch something here. This is our unknown, which we started with, which is the integral of cosec cubic x. And here again the same thing, the same unknown. So you end up with twice the integral is equal to minus cotangent x cosec x plus the integral of the cosec. It's known. This is an elementary function, and we said before you should know some of them. It's equal to the logarithm of cosec x minus cotangent x. And here it is. Here is your integral direct. So, and this is actually what we have done here. Instead of look at this step here, we can skip this step, and we can also skip this step, and we can directly end up with this step here, which is the integral of 1 of cosec square minus cotan, this minus belongs to cotan, time the second one without change, the integral of the cotan, time the derivative of the cosec, which is cotec minus cosec cotan, and the cotan increase the power by 1, and then you substitute for cotan square by cosec square minus, and then you end up with was the same integral, which is your unknown here, minus I, and then from the left hand side, twice the integral is equal to this expression, and from right directly you obtain your integral. Suppose you want to evaluate sine minus 1 x dx. Again here, instead of saying u dv and v du, directly you can directly do the same thing. All you have to do, in fact, you can put 1 directly. So here what I did, in fact, that I follow the same step, u dv minus v du. But suppose I do it, I try to do it differently, direct away. I put just here 1. So the integral 1 is x times the second one without change, minus the integral of 1, times the derivative of the other one, which is integral 1 minus x squared dx. And in fact, this is what? This is the second step here, we have it here, and this integral directly is equal to this, and you can do it by substitution. Take 1 minus x squared is equal to u, and you proceed as we have mentioned in our last lecture. So you see, you save steps by applying this fact directly. The product of the integral of the product of two functions is equal to the antiderivative of 1 times the second one without change, minus the integral of the antiderivative of the first one, same thing, times this time the derivative of the other. Here is the same thing. You integrate 1 plus x squared. You put 1 here. The integral of 1 is x times the second one without change, minus the integral of the first one, again, 1 gets x, times the derivative of square root of 1 plus x squared, which is this integral here. This integral is simple because this x squared divided by the square root. And in fact, the x squared by the square root, you can put it in this way. You can divide, and this is simple algebra. And you notice something, that this is the integral, this is the unknown which you started from. This is the integral which we seek to calculate. You find it on the on the right hand side. So you move it to the left hand side to obtain twice the integral is equal to this one, plus this integral, and this integral, as a fact, is one of the elementary, again, functions, which is sine minus 1x. Now, sometimes we encounter integrals of the form, for example, integral of sine to the nx dx. And they tell you, for example, calculate the integral of sine to the n, and then try to calculate, for example, sine cubic x dx. So you start by you wish to obtain a formula which is general to any n. So you do what you call a reduction formula. In this reduction formula, suppose this is your integral, in is unknown for any n, and you put it in this form. You decompose sine to the n to sine to the n minus 1 x sine x, and then you skip all that as we did before. You have the integral of 1 of sine, which is minus cosine. Here the minus belongs to cosine. Times the other one without change. This one without change. Minus the integral of minus cosine again, so you invert the minus into plus. Times the derivative of sine minus 1, sine to the power n minus 1, which is n minus 1, times sine to the n minus 2x, times cosine x dx. Now here you have to fiddle up with the algebra. You multiply cosine by cosine to get cosine square, and then you substitute cosine square by 1 minus sine square, and you end up with something like this. Now look at this final expression here. It's sine to the power n minus 1 x cosine x plus n minus 1 times what? Times two factors here. You got integral of sine to the n minus 2x minus the integral of sine to the n minus 2 times sine square. You got sine power to the n x dx. And in fact, this is what? This is integral which we started from, which we seek to calculate. And therefore, again, you proceed to move it to the left-hand side. So in order to get what? To get your integral is equal to this, is equal to sine n minus 1 cosine x plus this one. This integral, in fact, is what? Is the same one you started with, but it's reduced. Instead of n, you get sine n minus 2. So you have succeeded in bringing down the degree of your sine function. Instead of you are seeking to calculate the integral of sine to the power n in terms of the integral of sine n minus 2. And you keep doing this. Minus n minus 1 times the integral which you seek to calculate. So if you move this, which is in, to the left-hand side, you get what? 1 plus n minus 1. In other words, n n I n is equal to this integral, to this expression here. And end up, if you divide by n, you obtain I n in this form. You obtain I n in the form I n, this is integral of any sine to the power n, is equal to 1 over n minus sine n minus 1 x times cosine x plus n minus 1 times n I n minus 2. It tells you what? It tells you the integral of sine to the power n is given in terms of the integral of sine n minus 2. Suppose they wish to ask you to obtain the integral of sine cube. So directly you put here, substitute n is equal to 3. So you get I3 is equal to 1 over 3 times minus sine square x cosine x plus what here? N is equal to 3. Twice I what? I1 now. I1 is what? Is the integral of sine to the power n1 is n is equal to 1. So this integral is directly minus cosine x. So you put here minus cosine x and you get I3. Suppose I ask you to integrate, to evaluate sine to the power 5. You do the same thing and you try to obtain a relation in terms sine to the power 5 in terms sine to the power 3. And since you have a relation between sine to the power 3 and sine to the power 1, and this is actually how it goes. You try to reduce your formula and you obtain a formula which is valid for any n. This, in fact, it's called a reduction formula. And here it is. To calculate sine to the power 3, as we did on the paper, it's equal to this expression here. You reduce sine to the power 3 in terms of sine to the power 1, which we know that the integral of sine is equal to minus cosine. In fact, the same applies to, for example, sec to the power n. Suppose you wish to integrate sec to the power n for any n. Of course, if n is even, there are other ways. But if n is odd, there is no other way except the integration by part. So what you do is that you write sine to the power n in terms of sine square times sine to the n minus 2. And forget about u and v. You integrate one. Here you integrate sec squared to give 10. Times the other one without change. Here it is. Minus, again, the integral of what? The first one, the integral of the first one, which is the antiderivative of the first one, like here, 10x, times what now? Times the derivative of the second one. What is the derivative of sec to the power n minus 2? Is equal to n minus 2, sec to the power n minus 3, times the derivative of the sec, which is sec 10. This is the chain rule. And then here you notice something. You have 10 and 10, so you have 10 square. You substitute 10 square for sec square minus 1, and it brings you back to an expression of this kind here. You have here sec to the 10 minus 2 times 10 square. When you substitute 10 square for sec square minus 1, you end up with what? Sec square times sec to the n minus 2, which is sec to the power n, which is your unknown, the one that you started with, minus I n minus 2, sec to the power n minus 2 under the integral sign. Meaning that, and this is, you don't know, of course, but you have succeeded in obtaining a relation, gathering sec to the power n in terms of the integral of sec to the power n minus 2. And in fact, this is how it goes here. This is I to the power n minus 2, and here it is. And this is again what? N minus 2 times I to the power n, the unknown which you started from. So you have an In is equal to this expression, and from which you move this to the left-hand side to obtain an expression of this sort. And this actually is your reduction formula. Your reduction formula tells you what? Tells you that you have a relation between the integral of sec to the power n in terms of the integral of sec to the power n minus 2. So suppose, for example, you wish to calculate the integral of sec to the power 5. So all you have to do is you substitute in your expression by n is equal to 5. If n is equal to 5, you get what? You get what? You get, let's go to the slide before. You have I5, this is integral sec to the power 5, is equal to 1 over 4 times what? Sec to the power 3x tan x plus 3 times what? Times the integral of what this time? Sec cube, which is I3. But now how we're going to calculate I3? You use the same formula. It's equal to 1 over 2 times the integral of what? Sec x tan x plus the integral of, this time n is equal to 3. 1 times I1. What is I1? The integral of what? Of the sec x dx. But the integral of the sec, I know it because this is an elementary function. It is in the form of ln sec plus tan. So in fact, now what you do is that you will be able to calculate the integral of I to the 5 in terms of the integral of I to the 1. This is how you call a reduction formula, and this is how it goes. You keep reducing the order of your integral by a kind of reduction formula. Of course, this doesn't only apply this; it applies to all form of functions. Suppose, for example, they ask you integral ln n x dx. How would you do that? Same thing. You put here 1, so you get x times ln x to the power n minus the integral of x times the logarithm, the derivative of this, which is n ln x times the derivative of this 1 over x dx. So in fact, you reduced x to the power n in terms of what? I'm sorry here. You have the derivative of this one. Exactly, this go this way. So in fact, you will be able to reduce x to the power ln x to the power n minus the n, the integral of what here? Of n, you may directly call this I n minus 1, because instead of n you have I n minus 1. So you were able to obtain the logarithm of power 7, the antiderivative of the power 7 in terms of the power 6, and you do the same thing, 6 in terms of 5, and you keep doing that until you end up with the logarithm of x. But logarithm of x, I know, is equal to x ln x minus x, for example. And you do it, of course, in integration by parts also, because there is no other way instead of the aside from the integration by parts in order to calculate these kind of functions. And here it is. This is for sec to the power 5. For example, suppose you have an integral of this sort, sine to the m, cosine to the n. This is more complicated, but it exactly goes to the same way. Here, you decompose, for example, cosine. Same thing, you may decompose sine. So cosine to the power n minus 1 times cosine. So here you do, instead of the do a and v, again, you skip this step. You say the integral of what? The integral of the, look at this, sine to the power m times cosine x. This is the integral of what? It's integral, it's the derivative of sine to the power m plus 1 divided by m minus plus 1. Because when you differentiate this, you got sine to the power m cosine x, and this goes m plus 1, cancelled with m plus 1. So you integrate this product, sine to the power m cosine x, times the other one without change, minus the integral of what? This one again, times the derivative of cosine to the power n minus 1. While the derivative of the cosine power n minus 1 is equal to what? N minus 1 times cosine n minus 2 x. And then again here, what you do is that you decompose sine to the power m plus 2 into sine to the power m times sine square. But sine square is equal to what? Is equal to 1 minus cosine square. And if you realize here, the last expression here, it tells you what? If you carry out the multiplication, you get sine to the power m times cosine n minus 2. In other words, you have not reduced the power of the sine, but you are able to reduce the power of the cosine by 2. Minus the integral of sine to the power n times cosine squared times cosine n minus 2, which is cosine to the power n, which is the same unknown you have started with. So in fact, you are able to calculate, to obtain your integral, which you are seeking to calculate, your antiderivative, in terms of another one, of another integral in which the power m is not reduced by the n is reduced, or the contrary, or the opposite, exactly. And of course, you keep doing that. You keep reducing until you finish up with all the powers of cosine, and it remains what? 1 sine to the power. Suppose n is odd, and you at the end you end up, for example, with sine to the power m times cosine x. What is the integral of this? It's directly sine to the power m plus 1 divided by m plus 1, etc. So in fact, you are able to reduce your expression, your integral, your indefinite integral, which you seek to calculate, and it looks complicated. You seek to, each time you do a reduction process, you succeed in bringing the powers of what you would not be able to achieve into less powers in which the integrals are quite known. And with this, actually, you get a reduction process of this sort. Of course, this reduction process is quite complicated, but it gives you an idea of how you may be able to calculate antiderivatives of functions of this sort. Functions like functions of this nature, and with this we have what we have spoken about actually in this lecture. When you come out from this lecture, what as a resume, as what we have gained is to tell you that if you fail by the method of substitution, usually you try first the method of substitution, and then you keep on going. So you have integration by parts. As I said, the most powerful of all techniques, and this helps you in calculating many antiderivatives which you couldn't do by any other method. And there is no other way for calculating, for example, the integral of sec cube, the antiderivative of sec cube, of x dx, of cosec cube, or ln x alone, or x ln x, or any such product of two functions of different nature. One is x, the other is ln, one is e to the power x, the other one is cosine, one is x cubic, the other one is sine. All these kind of functions which you see that they are composed of product of function of two different nature, you must conclude that there is no other way out except through the integration by parts. And this is how it is done. And we have seen that Leibniz calculus were able to bring down the formula which we have been using at the very start of this lesson into a formula which is simpler. It's equal the integral of u dv is equal to uv minus the integral of v du, so long as both antiderivative exist. And this formula, in fact, is very much simpler, except for one thing, is that each time you have to check which is u and which is v. You choose u in such a way as when you differentiate it reduced in degree. Not that it increased in degree, of course. And then I taught you a method which is much simpler even. This is the way I tell my students about, is that when you have a product of two functions and you wish to obtain the antiderivative, all you have to do is that you say that the integral of this product is equal to the indefinite integral, of course. The antiderivative of this product is equal to what? Keep it in mind this way. The antiderivative of one times the other one without change. In other way, neither you differentiate it nor you integrate it. Again, the antiderivative of the first one, which is the first, it's up to you, one that is reduced in order. The antiderivative of the first one times the other one without change, minus the integral, of course, the indefinite integral of, again, the first one, the antiderivative of the first one, which is already located as the first term, times this time what? Times not the other one without change this time, but the other one differentiated, times the derivative of the second one. And from this on, you see, you directly have to say that if you are working correctly, that the degree is reduced, and from then onward, you can keep on going like this forever, not forever, but until you exhaust your degree, and from which you can get your result. At the end of this lecture, I wish to remind you that this lecture, like exactly the others which have preceded it, or the one that you're going to come later, if God wishes, are all uploaded to the site of the Magnitude project, which is administered by the consortium Nettuno in Italy for distance learning. And you can subscribe, of course, to these courses. You can see them, and you can also have acquaintance with the professors, and also you can get into all the exercises which are offered, and each exercise coincides with a particular lesson. And you can subscribe for your certificate if you wishes to. Again, until we meet then for a next method of integration, which is the one we're going to speak in our next lesson, I wishes you good luck, and I thank you for your attention. Thank you very much.